Hello community, so great that you are back. We have a new Llama 4 model and today we look at the smallest little Llama 4 called Scout. Scout is special, it has a 10 million token context length and you know what? It is real easy how it achieves this performance. And you know, Meta published here 2 models here and we looked already here. I have 2 videos where I looked at the performance here in a real world logic test on Maverick, our 400 billion trainable parameter model. But today we look here at the little brother at Scout. Only with 109 billion total parameters, you can have this in an integer 4 quantization on a single NVIDIA H100 GPU. But you know what? Llama Scout was both pre-trained and post-trained, not with 10 million context length, but with 250,000 context length. And I was now interested at how is this possible? If the system inherently only has 256K, how is it now possible 10 million? Now, it is easy. Let me explain. You remember the softmax function that we have in the self-attention layer we apply to a vector like the attention logics. Here we have this vector, and in the simplest case, I just go with 3, 2, 1. We calculate the exponential, the sum of the exponential, and the softmax, the result of the softmax is now, for the 3, we have here 0.6, for the 2, we have 0.2, and for the smallest one, we have 0.09. So you see, the highest logic, here the 3, gets a softmax output of about 66%. So it clearly stands out from all the other. We have here beautiful, if you want, performance, a resolution that tells us here, this is it. And you know, the softmax transformation here transforms any set of number into our probability distribution that we are looking for here at the end of our vector structure. Now let's make it a little bit longer. Let's say we have 100 elements, no? And we're not near anywhere of 10 million token length. No, we are just going here with a simple logic vector, and we have one element is a 3, our same 3, and the other 99 elements are zeros. Now we do the calculation, and we do the sum of the exponential, and now the softmax output is different. Look, for the 3 we have now 0.16, and for all the other is 0.008. So even though the 3 is still here the highest value, its probability now drops significantly to about 16% compared to the 66% in the short context. And this is because of the presence of so many other numbers. They are also real small. So this increases now the denominator of the softmax function, making here overall the distribution flatter. And this signal does not become as clear as before. And this causes now the problem. So if a Llama 4 wants now to handle here very long context, and let's say 10 million token is for me already long, then the attention score produced here by the classical softmax function flatten, real down. And the model fails to emphasize here the most relevant part of the information. We know this phenomenon here on all models as an attention fading mechanism. Now the question is, what can we do? Is there any solution at all? And as a subscriber of this beautiful YouTube channel, you know, yes. 1 year ago, I showed you the solution here by UC Berkeley and Google, ring attention. For 1 year ago, we had already infinity context length or 1 million context length by Google. But you need the infrastructure, no? Or I showed you also almost 10 months ago here, recurrent LLM, the next gen AI, recurrent Llama, for a long context, and we talked in detail about how they achieved this with Google. But now we are here with Meta. And Meta now, Llama 4, does something really interesting. We have here this publication here, end of January 2025. Scalable softmax is superior for the attention. And here, Ken is from the institute, the University of Tokyo, Institute for Physics of Intelligence, and Ken found a solution. You just have to modify here the softmax function, the mathematical function. So you go from the classical softmax and you just modify it a little bit. And with this scalable softmax function, you get now the perfect resolution, the perfect performance. It does not flatten out. Look here, in blue you have how it goes down in the classical softmax function. And here in red you see here the real performance. It stays here. You can really discriminate here all the logics that we are looking for. Perfect. So thanks to Ken, this works. But Ken said, okay, but let's check this here, no? Let's go here with the needle in a haystack. So softmax for some model sizes here on specific LLMs, he calculated the classical softmax. And you see in green, okay, but then look here, the rest is red. This is all red, it's not finding anything. But with the new scalable softmax, look at this, green, almost to the end. Isn't this beautiful? Yeah, and there are a lot of more mathematical data and benchmark data. If you're interested, I highly recommend here, if you want to have a deep dive into mathematical calculation, and it also shows why this is really a very good way, maybe the best way here for scalable softmax. Have a look at this paper. I highly recommend this paper. But you know, self-attention, you know if you're a subscriber to my channel that there's positional encoding, no? But luckily we have two beautiful videos here, and I showed you here rope in all its beauty and glory. If you go from an 8K to a 4 million context length window, we went through everything: interpolation, kernel, yarn, long rope, theta scaling, ring attention, and I even have a second video if you really want to go here with a theta scaling that is beyond what we do normally. This is more than 6 months old, this video, but it explains here, to best of my knowledge, how I see rotary position embedding. And now Cohere, also at the end of January 2025, a very productive January, I have to say, Cohere gives us here now the solution. And Cohere has now a new hybrid attention strategy. And Cohere shows us here rope to nope and back again. So you immediately understand, hey, this hybrid attention strategy is here a mixture of rope and nope layer. Nope stands simply for no positional embedding encoding in those layers. So therefore, you say, now I understand how we can go to 10 millions. We just mix here the rotary position embedding with layers of no positional embeddings, no? Exactly, and they found that the mixture is not as simple, but you have rope and the no positional embedding, nope, and you have to do a normalization, a very key normalization. And they identified here the strength and some shortcomings in this long context modeling. So thanks to Cohere and the researcher from Cohere, we found here end of January this solution. And guess what? Yes. Yeah, Cohere, they say here, we propose here a novel architecture based on a hybrid attention mechanism that not only surpasses here the conventional rope-based transformer in a long context task, but also achieve a competitive performance on the benchmark requiring here the shorter context length. Because if you go, remember this one here, this is from May 2024, this is here from Shanghai, China, the university, the length generalization of causal transformer without position encoding. And we had a look at the time at this expanded nope functionality, where we were tuning here a parameter efficient tuning for searching the attention head's best temperature hyperparameter. And they found out here, Shanghai, thank you, that they can expand here the nope context size massively if you do here the hyperparameter optimization. This is, of course, they published this here on an MIT license. You can see only 22 stars, but you know what? It is so important here for the development of Llama 4. So this shows you, even if you go to a GitHub and say only 2 watching and 22 stars, yeah, but you know, sometimes this is exactly what you need if you want to push ahead to the next generation AI models. And this is all we need. Here we are, summary. So what we do? We take here from the very first part of this video, the Inference-Time temperature scaling, our beautiful new softmax here. We're scaling the largest here with a factor depending here on log n. And we have now a weapon that we can fight attention fading in long context. This is done in Llama 4 massive context windows. But we have to add now together here this hybrid attention strategy with Node from Cohere. So thank you to University of Tokyo and thank you to Cohere. We have now our two tools that are powerful. And guess what? If I add these two tools together, you know what? I get now the new intelligent rope that by Meta, a new branding, that is exactly this. University of Tokyo and Cohere, and they implement these ideas and they give it your own brand name, so you would say, hey, wow, Meta developed this. Oh no, this was the open source community, and they are pushing ahead. And now, these two technologies now contribute here to Llama's 4 ability to generalize the context far beyond what is its pre-training and post-training, the 256K, and they can go now to extreme long inputs, especially with this NOPE interwoven layer. So this interwoven layer structure is really great. And if you do a needle in a haystack test, you see here the Llama 4 Scout, so the small model with 10 million tokens. Look, a context length of 10 million. And yeah, it looking great. This is perfect, no? Isn't this amazing? And you might say, yes, we achieved it. Llama 4, 10 million token context length. Great. But you know my videos, no? And I say, wait. No, at first I say thank you to all non-subscribers. If you're new to this channel, I think this is the end of the video for you. Thank you for watching. It was great that you were here. But for my subscriber who know me, who know we're doing here some science and not just some PR for Meta, you know that the question remains, is finding a piece of information already equal to reasoning with this piece of information? This means, is Meta really able to have a causal reasoning chain, a chain of sort, or is it just about finding here the needle in the haystack? And is this equivalent already with a reasoning capability? And you will be surprised if I tell you. The second part of my video is about, if we go to a full large language model context window, we fill up 90% here of all the tokens, we have a reduction in the performance of the system of 75% for reasoning. So, careful. It is perfect in the needle in a haystack. It finds something, no? But the moment you want to argue on a piece of text that is real huge, you want to have a causal argumentation, you want a system understands it and deducts here some logical answers, be aware that you could lose, in the worst case, 75% of the performance of the system overall if you fill up your context window. And you might say, is this true? Is it really possible that a full context window leads to LLM reasoning degradation? And you might say, what little, I don't know, general universities somewhere here in the outskirts of Idaho had this crazy, okay, MIT. We have a new publication, MIT, April 2nd, 2025, exploring here the LLM reasoning through controlled prompt variations. MIT is looking at this. Interesting. It's a little bit late. It is not the latest because if you look closely, you will see the data are already some months old. But okay, let's be generous. I selected this publication because I want to show you one fact. Do you remember this one from October 2024 by Apple, GSM Symbolic, Understanding the Limitation of Mathematical Reasoning in Large Language Models? And their findings indicate that LLM often rely on pattern recognition alone, and they're doing not a true logical reasoning. They just discover a pattern and they found an answer in their training data to this particular pattern, and they understand nothing. And this is what an AI is, no? It is a pattern recognition machine. But we want that this is here super hyper intelligent that does some true logic reasoning. So this was a little bit of a drawback by Apple. Said, hey, what does Apple know about general intelligence? Nothing. So this GSM Symbolic explored the impact of problem statement variation. But what if, and now just a question, a very innocent question, what if we are focusing on noise perturbation within the context window? So we don't go as far as Apple did to have a problem statement variation. No. We just add a little bit of noise to our prompt. Would this make any difference to our super hyper intelligence Llama 4 models or our large language models? And now this study aims to analyze, investigate how different perturbations affect the reasoning capabilities of LLM. Not find the needle in the haystack, but the reasoning capabilities. understanding how this LLM react to different forms of input perturbations. And they discovered that this is here like a flashlight. You can look inside the black box here of an LLM, discover the internal reasoning processes. Yes, there was a beautiful paper by Anthropic about this, but here, this is even more interesting, no? Now, you remember that we had also a GSM Plus, no? You know this as a subscriber. University of Hong Kong 10-center AI lab here. Comprehensive benchmark evaluating the robustness here for mathematical problem solver. And they found LLMs can make mistakes when new statements are added or the question targets are altered. And this was interesting, no? Just add a sentence and suddenly the system is not able to solve it anymore. How is this possible? Our AI is intelligent, no? So let's open up now this second part here of this video and I show you here, this is what we're going to look at. We have a question and we have an answer. And this is from our standard mathematical data set, our training data set that millions of people use, no? We have a predefined training data set. Claire makes 3 eggs omelette every morning. How many dozen of eggs will she eat in 4 weeks? And we have an answer, and this is the answer that we want. The AI learns. This is the correct way. But what would happen if we just modify here the training data a tiny, simple bit? Let's look at these models. And MIT checked out those models, and you see, yeah, this is not the latest one. We still have the 3.5 Sonnet and not the 3.7 Sonnet. And we have GPT-4 Omni and not the O3 Mini. We still have O1. But okay, so it's a little bit some months old, but in general, just look at the Llama, the 3.1, the 3.2. I will show you something. To what extent can those models reliably perform complex reasoning when confronted with a little bit of a noisy input? So we have here our spark of genius, and you say, okay, let's be the advocate of the devil, no? So you know, this is our training data set. This is our grade school level mathematical problem data set for multi-step reasoning. This is classical. We find this everywhere, Hugging Face. We have here even a training data set and a test data set. And here you have all the examples. So we have real simple problems here, plus the solution, how to compute the solution. Eh? Everything is here. Every model has been trained on this. This is standard. And now the core idea is based here on one of 4 other papers. And this is what the first I'm going to show you. This is from 2023. You might say, my goodness, 2023. But they found that LLMs can be easily distracted by some irrelevant context. And we do this now. We say now, Claire has still 3 eggs omelette every morning. How many eggs? Dozen of eggs will she eat in 4 weeks? But now we add some irrelevant context. Below is some context you might find useful for answering the question above, and we have a Wikipedia page, how, I don't know, whatever is about eggs or whatever you have, or some financial docs, you know, some irrelevant document. But this is what you also get typically from a RAG, from a retrieval, augmented prompt that is then fed into our generation LLM. No? So this is really interesting. And now they say something, you know, we take this and we occupy now up to 90% of the specific model context window, what we just looked at the first part of this video. And we just fill it up to 90%. But you know, we have one question and just nonsense. So no problem, we have a perfect needle in a haystack. And then we have some pathological cases. And the pathological cases arose from this publication in 2021. This Allen Institute of Artificial Intelligence here, improving the consistency in pre-trained models. Great, I'll give you an example. Here, add the name of a color before every adjective. It's pathological. It's absolutely nothing to do with it. Yeah? Would it have any influence on the reasoning capabilities? And then we have your drop. Reading comprehension benchmark here. Now we have more relevant information. So in our example here, we blow it up. Now we say Claire, now a fitness enthusiast. Now 3 eggs omelette every morning for breakfast. Now we put in more relevant information to fuel her active lifestyle. She believes in starting her day with a protein-rich meal to keep her energized through the day. How many dozen of eggs will she eat in 4 days? And then consider whatever. So relevant information. Also, you can get this back from RAG. No? This is a typical RAG answer. And we do not fill up anything. We just provide here, like here, some additional, a couple of statements now, extracted here by RAG, imagine this, to have here more information for your LLM. Will this have any implementation for the reasoning capabilities of LLMs? Is what MIT asked. And then even a case where you use here a combination of the pathological and the relevant information. You see here the pathological is here in blue, add the name of a color before every adjective, just makes no sense. And the relevant information is just what we looked at. So those 4 cases of noise in the prompt were now examined. And you know what? Our beautiful mathematical data set has this inherent ability. It needs multiple reasoning steps. You see, we have a peak here at 3 reasoning steps, but we can go here statistically to 5 or 6 reasoning steps. So this is beautiful. This is what we want. No? We want not just problem answer, we want some reasoning step. We want to see the reasoning process of this LLM. So let's come here to the result. It's so nice, no? MIT tells us our findings highlight here critical vulnerabilities in the current LLMs from the last 2-3 months and underscore the need for improved robustness. And you might say, why? What are the results? Now, temperature setting was 0.2, maximum token limit here was 2K, but look at the result. Here we have our 4 pieces, no? Our irrelevant, our pathological, our relevant prompts, and the combination here of relevant and pathological. And then we have the average of everything. This is now really interesting. Now, you see irrelevant information added in your prompt can have here a massive impact on the performance of your model. For example, here, a Mistral 8x22b. This is an old model. This is not the latest actual Mistral model. This is an old model. But this old model went down 78% of the performance. If you fill up 90% of the model context window, this is only for the irrelevant part. But a Mistral 7b went down 40%. A Meta Llama 3.1405 billion went down 50%. A Llama 3.18b went down 75%. And a Llama 2, now we have Llama 3, so this is an old model, Llama went down 83% just by filling up the model context window. And a Llama had a very limited context window in tokens. No? Even a Command R Plus, you see, this is here from mid of 2024, had a performance drop of minus 67%. So what is happening here? In pathological, you see, because we just added here very short information on pathological information, it was not as harsh. Minus 16%, minus 15%, minus 20%, minus 22%. That was okay. But why we do have this at all? What if we add relevant information? You might say, this is good, this is RAG, no? We want more relevant information to our query, that the LLM has more information about it. Look, even a Claude Sonnet went down 4%. Command R went down 10%. Llama 3.23b went down 20%. And you would say, what is happening here? Yeah, and then the average, you see, that's not really great, no? What does it tell us? More information, even more relevant information in your prompt to the LLM is not always the solution. And more irrelevant information, if you say, yeah, the answer is somewhere in the book. So I download here the book in the prompt, I have, 10 million tokens, and then I want the LLM to reason about the content of the book. Guess what? Minus 78%, Llama, minus 75% performance, reasoning performance. So this is not the way to go. So I just wanted to show you this now. And you thought, okay, no, this was not the real picture because you have to go down on a model level. You have to go down to the reasoning steps. because they are not behaving all the same. You cannot have a general statement. Look at this. Again, this irrelevant part. Yeah? We just fill up 90% here of the total context token length with irrelevant information. So the LLM should say, hey, I just ignore this nonsense. No? I answer my query I was trained on. O1 is the best one here in this training set. It goes down, I don't know, just minus 10%, but just at 4 reasoning steps. No? At 5 reasoning steps, it's back to 0 reduction in the reasoning capability. O1 is not impressed if you add 90% of irrelevant information in the context window. GPT-4 Omni, this is not the latest 4 Omni, this is a Omni that is some month old. GPT-4 Omni had an interesting performance. It started at minus 20% for 2 reasoning step, went down to minus 60% for 3 reasoning step, went further down to, I don't know, close to minus 80 for 4 reasoning steps, went up to, I don't know, minus 70% at 5 reasoning steps, and then at 6 reasoning steps, it's just minus 100% performance degrading. And it stayed there. It is amazing. We don't know why this is happening. This is all the training. This is how the training data were fed to the system. This is the content of the training data, the quality of the training data, in the pre-training, in the supervised fine-tuning, maybe reinforcement learning. I think GPT-4 is beautifully showing you this here. Again, this is not the latest GPT-4. They are continuously improving this because, of course, they understand what's happening. Yeah? Mistral, also in green here. 2 reasoning steps, minus 40%. Down, down, down. But then look at this. 6 reasoning steps, suddenly it's back to 0 degradation. How is this possible that at 6 reasoning steps, somewhere in the training data set, this is what I assume, there were so many good examples that here Mistral 7b said, hey, I found immediately the solution. I'm not distracted here by this irrelevant information in my prompt. I can handle it. Amazing. But we lack a deeper understanding why this is happening. You can look here at the relevant information. You see each model is special. Pathological information, each model is special. And the combo, yippee, all over the place. So you see, what do we know about the reasoning capabilities if we fill up here irrelevant information? We have no understanding what's happening. We are looking at it, we say amazing, but we have no deeper understanding why. And this, I hear, quote, MIT highlights a crucial insight. The model's performance is not determined here by the amount or by the complexity of the information, but rather by their ability to identify and disregard non-essential details. So it is not okay if you just drag in, I don't know, complete libraries. Because your little system, and I showed you here, maybe a Llama 3.1, is in no way able to handle these long context windows and do a reasoning about it. So there you have it. I hope you enjoyed it a little bit. I hope you had a little bit of fun. This is really from the leading and bleeding edge of AI research to show you we have almost no idea what we're doing, but man, is it an interesting time to have some interest here in AI research, to see where research is going, and to have some brand new ideas to solve here. And I think Llama 4 is here a beautiful example that you see with some simple modification in softmax and some simple layer inserted here, rope, node, and then some normalization. You can achieve a 10 million context window. But what about the reasoning performance? More about it in my next videos.